Hello everyone. So let us start today with the sp hybridization. Sp hybrid orbitals are formed by the intermixing of one s orbital and one p orbitals. These s and p orbitals will have a comparable energy difference, giving rise to two identical and degenerate, that is at the same energy level the hybrid orbitals are formed, and this hybridization is known as sp hybridization. The percentage s character and p character in sp hybridization is 50 percentage. 50 percentage s and 50 percentage p, and these hybrid orbitals are arranged linearly by making an angle of 180-degree angle. So the arrangement or the geometry that we get for sp hybridization is linear. We can take the example of beryllium chloride. First let us consider the s orbital with intermixing with the p orbital. So it is of the same atom. Okay, if we take beryllium, so beryllium configuration, if we write 1s2 2s2, so one electron from 2s jumps to the higher energy level, that is p orbital. So we have two orbitals. Now the energy difference between 2s and 2p is very less, so these two orbitals can combine and give the formation of a hybrid orbital. So this is known as sp hybrid orbital, and the remaining p orbitals remains as it is, that is empty 2p orbitals. So this sp hybrid orbital is formed by the combination of s and p of the second shell, 2s and 2p. So 1s and one orbital of s and the one orbital of p intermix or hybridize to give the formation of two sp hybrid orbitals. So here we get the formation of two sp hybrid orbitals. Simply if we show the hybrid orbitals of beryllium, it is this bigger lobe and here we have the smaller lobe. Similarly, this bigger lobe and the smaller lobe of the beryllium shows the hybrid condition or hybridization, hybrid orbitals of the beryllium atom. Now the beryllium atom can overlap with the atomic orbital of other atom. So let us see that beryllium chloride, beryllium in its isolated state. If we want to see the energy difference, see, we can see here, this is at this energy level, 2p is here, and in the excited state it has one electron in 2s and in one electron in 2p. Now when this hybridize, 2s and 2p electron of these two orbitals intermix, it gives the formation of hybridized beryllium atom. You can see the energy level, 2s is here and 2p is here, so the energy will be in between these two. So we say that all the characteristic will be similar, the shape will be similar. Now it will not have a spherical shape or dumbbell shape. It will be directed in space in such a way that repulsion is minimum and the stability is maximum, with the minimum repulsion between these two hybrid orbitals. So these are the two hybrid orbitals, one hybrid orbital and the second hybrid orbital. Now chlorine is the atom which is attached with this beryllium atom. So chlorine, if we write the atomic number and the configuration, we know that it is a group 17 element. So it has 7 electrons in its valence shell. It is 1 electron lack of the octet, right? So that combines, that is we have chlorine, if we write the configuration, neon, from neon if we start, or if we write from the beginning, it is 1s2 2s2 2p6, that is neon. After that 3s2 3p5, so 1 lack of octet. So that combination, this is the p orbital, dumbbell shape of the p orbital, and it forms a covalent bond with the hybrid orbital of the beryllium. This is the combination, right? The hybrid orbital of beryllium overlaps with the atomic orbital of the chlorine, p orbital, that is, okay, and gives the formation of a beryllium chloride molecule with the bond angle of 180, and the structure is a linear structure. If we consider the combination, the beryllium chloride has the combination of sp and p orbital, that is sp of beryllium overlaps with the p orbital of chlorine. So it is sp and p, sp p overlapping. The geometry is linear. Hybridization is sp and the geometry is linear geometry. Geometry is linear. So according to the conditions or the characteristics that we have studied, we know that the hybridization gives the regular geometry to the molecule. So classical or standard or regular, what we say is, the sp hybridization gives a linear geometry to the molecule. Next we will see sp2 hybridization. Thank you.